Hi, and welcome to this part 3 of our lesson 8 video that's all about the drill press. And today we're going to carry on where we left off last time, and that is with reamers. For two reasons. Well, the first is that we weren't done covering the subject. And the second is that something seems to have been misunderstood by a few people. And that is the difference between margins on a drill and the cutting edges margins on a reamer. So let's head over to the whiteboard and take a second look at that. So we have here a representation of a drill and a reamer. And what we're looking at here is the margin in the drill's case and the edge of the cutting lip, the one that is all along the flute of the reamer, and we can see that this one comes to a point whereas this one doesn't. Now what's the difference? The margin on a drill is the diameter of the drill. It has no clearance. So if I took this margin and stretched it out all around the drill, I would get a nice circle. There's no clearance. It is round. Whereas with the reamer, we have a real cutting edge. And it's my fault if there's some confusion, because I have a tendency to call this a margin anyways, but it isn't. It's a cutting edge. So the tooth all along the flute of the reamer is a cutting edge. We have an edge, a point that comes right at the major diameter of the tool, and everything after that is in relief. So that means that this point can penetrate the surface, and that makes this a cutting edge, whereas this margin that is round and cannot penetrate the surface is not a cutting edge. And why is that so important? The answer is quite simple. It's quite long, but it's quite simple. And that is, what is the tool used for, and how does it work? Well, the drill is used to produce a hole completely. It is center cutting. It works by cutting right to its center, and that's what the chisel edge is there for. Whereas the reamer is used to slightly enlarge a hole that already exists. It's not made to produce completely a hole, and there is no chisel edge or center cutting action on a reamer, because you can't have those equal on both sides and still get something that's accurate, because this tool, the drill bit, is center cutting. If it had a cutting lip on its edge there, well, something would have to give, because you can't have one thing and its opposite at the same time. There has to be a boss, there has to be a leader, and in this case, the leader for keeping the drill bit on track is the chisel edge, coupled with the angle of these chip producing cutting edges here. But that has nothing to do with the margins. Whereas with this tool, the reamer, it's the end cutting lips and the margins themselves that keep this tool tracking in the hole that already exists. Very different ways of positioning and keeping the tool in line. Now, why is it important for the drill to have a margin that is not a cutting lip? Well, since the chisel edge is keeping this tool on center, if we had a cutting edge there and we want to be able to retract and insert a drill many times if we're deep drilling a hole, well, as long as the cutting edge is keeping the drill, the chisel edge is keeping the drill tracking down its hole, all is well. But when we pull the drill out or insert it into a hole to go back to the bottom to keep on drilling, well, we often hear a little bit of chatter. And that's because as soon as the chisel edge isn't doing its job of keeping things aligned with the angles of those cutting lips, keeping everything tracking nicely, Well, the drill goes to where it naturally wants to go, and that means that one of the two edges of the drills is probably going to be rubbing. Now, if these were cutting edges, the minute that the chisel edge would stop tracking the drill in the hole, they would start cutting and grabbing, and that little chatter that we get would become a huge chatter problem, and it would be enlarging the hole. Whereas rounded out margins that don't cut, well, they tend to keep the drill in the hole, and even if it rubs on the side, it won't enlarge the hole any more than that. So why do these margins have to be sharp if they're not a cutting edge? Well, they have to be sharp because if they were rounded out and not have a sharp edge on them, chips would easily get stuck between the margin and the inside of the hole, and that would obviously jam everything in place. So they have to be sharp, but they are not cutting edges. We want that edge to be able to rub without enlarging the hole. Why? Because we're center cutting. And Jim, out in Greenland, now I always want to say Groenland because in French we say Groenland for Greenland. But Jim, out in Greenland, your question about retracting the drill in a deep hole. We want to retract the drill rapidly from a deep hole, as rapidly as possible. Not because we're afraid that chatter on the margin is going to enlarge the hole. It's more a question of keeping the temperatures down due to friction. And obviously these rounded margins do rub, especially when you're retracting and inserting into a deep hole, and that creates a lot of heat. So to avoid that heat, I recommend you pull a tool out as quickly as possible. If your lathe can do so, well, pull the whole tailstock back, as we did in the hammer handle project video. But don't make yourself sick over it. You now know that your margin won't be oversizing your hole because it's not made to cut. And if it does rub, well, just use a little more coolant. And remember, coolant is for the tool, not for the part. So if you're putting coolant when you're drilling, you have to try and get it into the hole to cool your tool down. And if not, well, retract the tool as quickly as you can and cool it down with coolant. I hope that answers your question, Jim, and I hope it's nice up in Groenland. I'd really like to visit there someday. So let's get back to this. We now have an idea of why the margins here are rounded out and why we have our chisel edge there to track. Our reamer doesn't have that. It has a 45-degree angle on its end. Remember, we saw that in the part 2 video of this lesson 8. And it's that 45 degrees that keeps the tool tracking in the hole that it's penetrating into. So why is it so important that we have cutting lips here? Well, because we want the hole to be as close to the diameter of the reamer as possible. And for that, well, you have no choice. This edge has to be a cutting lip because it's going to just come and just lick those edges clean as the tool goes in, and obviously you cannot have friction. So how do we reduce friction here? Well, we keep it very sharp and at a cutting edge. If this tool actually cut a hole its exact diameter, this tool would jam into that hole. It's not a problem because drills, as mentioned before, always cut their holes a little oversized. This tool is made to lightly shave a hole bigger and to maintain the best diameter possible. And for that, we need this cutting edge. But that also implies that there's a major difference in how we use both these tools. And there is a major difference. We do not use a reamer at all in the same fashion that we would use a drill. So how does using a reamer and using a drill bit differ? Well, here I have a 7/16 straight flute reamer. And here I have a 7/16 drill bit. Feed, speed, and technique. That's how it differs. So let's take a look at feeds. For this drill bit, I want to maintain somewhere around 2.5 to 3 thousandths of an inch in feed for every rev or revolution of the tool. So that means that each of the two cutting lips on this 7/16 drill bit is going to be picking up about 1.5 thousandths of an inch in thickness of material for each revolution. For 3 thou total, because there's two cutting lips on its end. This reamer has 6 cutting lips, and larger reamers could have up to 8. Well, obviously, if I want to maintain the same chip load, and I do. What is a chip load? It's the thickness of chip per tooth. So this drill bit was picking up a chip load of about 1.5 thousandths of an inch. This, I would like to maintain that chip load. So if my feed here was 3 thousandths of an inch per rev, and I have 3 times the number of cutting lips on this reamer, well, I'm going to be 3 times the feed to maintain the same cutting tooth or chip load. Sorry about that. So chip load, great stuff. So if I'm feeding at 3 thousandths of an inch here, I'm going to want to feed at 9 thousandths of an inch per rev with my reamer. So feed is quite different. What about speed? Speed is quite different also. And it has more with control of the tool and reducing chatter than it has to do with the actual proper speed. So what do I mean by that? This drill bit, to use it, we would use our classic formula, a cutting speed times 4 divided by diameter. And we've spoken about that formula many times. So that would be how we would calculate the speed for this drill bit. For the reamer, I would use the same formula, but I would reduce the speed by 1/3, or would run the speed about 1/3 of the speed that I would run the drill at. So if I calculated, and I'm just imagining here that this drill was turning at 300 RPM, I just chose 300 to make it simple for my feeble little mind here, 300 RPM, well, I would want the reamer of the same size to be turning 1/3 of that speed. So that would mean that I would ream the hole at about 100 RPM. And I said that has more to do with control and a lack of chatter. The faster a tool turns, the faster it has to feed to maintain the chip load. If we think about it, we're talking about distance per rev for our feed. So the faster that the tool turns, the faster you have to feed to maintain the chip load. Well, that's all fine and dandy, but with the reamer, it moves seriously fast. If I ran the reamer at the same speed that I ran the drill bit at, I would have to feed phenomenally fast. And feeding that fast, well, has control problems. It has control problems for engaging the tools, and it has control problems for stopping the feed at the proper moment. So if I want some control on my depth of feed and my speed, well, I'd better reduce the RPM so that I can maintain my chip load without having to feed at an incredibly high rate. Well, that's fine for the control. What about the chatter? A tool that turns at high RPM has more possibilities for chatter. When does chatter occur? When the tool starts into the part and once the tool gets to the bottom of its cutting action. Not the bottom of the hole. Remember, this reamer never touches the bottom of its hole. That's when chatter occurs. It's when I stop feeding that the side teeth on this reamer can start gouging in. If I'm turning at a very high RPM, that problem is accentuated. So to reduce the chatter problem, I reduce the RPM. Imagine, I'm feeding into the part at a high rate because it's a 6-flute reamer, and I get to where I want to go. I stop feeding. Normally what you'd want to do here to avoid chatter is as soon as you stop feeding, you stop the machine. Now you know as I do that machines don't stop instantly. They have a certain energy accumulated in the mass of its moving components, and that means that it's going to take a while to stop. Now if you're turning at a very high RPM, well, it could take many RPMs before it slows down and stops. If you're turning at a lower speed, well, it will stop faster. And that's another reason why. Because when you're cutting with a reamer, you want to cut or feed into the part, but as soon as you hit your depth, you want to stop the machine from turning, and then you're going to retract the tool without any rotation, thus ensuring a total lack of chatter. And as far as technique goes, well, here's a couple of clips that show proper technique for deep hole drilling and proper technique for reaming. They were taken from my hammer handle video that you can find on my website, THATLAZYMACHINIST.com. Remember, everything on the site is free and it always will be. So here's those clips.
As I've mentioned several times before, when you start a drilling cycle, you can drill up to 3 times the diameter of the drill in depth without retracting. But if you go past that, well, you're going to want to start to perform a peck drilling cycle. So retract, cool, flush your chips, and drill again. Note that the deeper that you get into the part, the shorter that the cutting period becomes. In other words, when the drill is in the part quite deeply, you don't want to leave it there for a long time, because when it is in the hole, it is rubbing, and that creates a lot of heat. So the peg drilling cycle accelerates with depth. So the drilling is done and we can move on to our reaming. But first, we have to adjust our speed. So that's the speed we were using for drilling. I'm going to reduce to 1/3 of that speed for reaming. A bit of lubrication is always a good idea. And note here the feed. I'm feeding at about the same rate that I was feeding at when I was drilling, but I have reduced my rotational speed to 1/3. And that means that I should have increased my chip load by quite a bit, which isn't a good thing. However, this tool has 6 cutting lips, and that means that my chip load remains about the same in both cases. Note also that in this case I'm retracting the tool rapidly rather than stopping the machine before retraction. I can do that because this hole is quite shallow. If the reamed hole is quite deep, really I recommend stopping the machine first. And finally, to protect the leading edge of the hole that I just reamed, I'm going to perform a small chamfer. That really recesses that edge into the part and protects it from any bumps or nicks.
Well, as you can see, the technique is quite different. But there's something else that you may be wondering about, and that is, what about small holes when they have odd sizes? Well, remember, if you can find a drill of a certain dimension, you can find a reamer of that same dimension. And you can even get reamers made to odd dimensions or specific dimensions that you require. But be advised, that gets very expensive. Here's something I think would be nice to look at, and it's a set of reamers that I used to use that were in my toolbox when I was teaching. And well, I don't have them anymore, so here's a picture of it because they didn't belong to me. I had to leave them at the school. I say that because really it's a tool that I found quite lovely. I mean, it's such a nice tool, this set of reamers, that it almost gets me physically aroused. But regardless, I don't have them anymore, but here is that picture. And it looks like a normal set of reamers until you scan down a little bit and see that it's an under and over size reamer set. And what does that mean? That means, and this is a fractional set, that means that for each dimension of reamer you have a thou over or a thou under. So if you have 0.5 dimension, you don't have a 0.5 reamer in this set, you have a 501 thousandths of an inch or a 499 thousandths of an inch reamer. That is lovely for doing work when you need light press fit or light clearance fit. You're playing around with dowels for punch and die sets or fixturing or whatnot, molds. It's great to have. It's lovely to have because you can really play with your different fits. And that brings to mind that I do have a video on fits, so if you have no idea what I'm talking about when I'm talking about a light press fit or a running clearance fit or a light clearance fit or whatnot, I do have a video on fits, an introduction to basic fits in the shop, how things fit together in other words, and the different classifications. So here's the name of that video, and it also can be found on my website. But there is still one thing that I want to present for the reamer section of our video on drill presses, and that is hole size, because as I've already mentioned, size does matter. And with reamers, we've seen that we have to pre-drill a hole. We're just making the hole a little bigger. And it would be logical to think that there is a specific sized hole for each size of reamer, because there is. So here's how I go about it. My suggestion is quite simple, a lot simpler than what you find in most books, and that is 5% smaller. You want the pre-drilled hole to be 5% smaller than the hole that you're going to ream. So let's head over to the whiteboard and take a look at an example of that. Well, here we have two examples. We're going to want to ream a 1/2 inch diameter hole, so 0.5 inch, and our second example will be for reaming a 6 millimeter diameter hole. Now, I said a 5% smaller, and all we have to do really to find out what 5% is, well, we measure whatever our diameter is by 0.05. So 0.05 times 0.5, that gives me 5% of 0.5. But I want 5% smaller than my 0.5. So that's why I say 0.5 minus 0.05 times 0.5 brackets. That will give me 5% smaller. And that's what I have here, a diameter of 0.475. That is, as far as I'm concerned, the proper diameter for reaming a 1/2 inch hole in most materials. Now, we live in the real world. This is a calculated number. In the real world, we have to find a proper drill. Well, the closest that we can get to 0.475 in our standard imperial sets, well, it's 15/32 of an inch, and that's reasonably close. But even better than that would be to use a 12 millimeter drill. And that is almost exactly what I want for my 0.475. So you calculate your diameter, and then you choose the closest drill to it that is slightly smaller. You don't want to go larger, especially if you're using a small tap. Now, this isn't how it is described in most books, and that gets me pissed off. Because the reason that most books apply the old rule, and I'm not even going to state the dimension properly, but it said something like, smaller than a certain dimension, you want to drill a hole a 64th of an inch smaller, and larger than a certain dimension, you want to drill a hole a 32nd of an inch smaller. And that was the basic rule. And the reason why that rule was applied was that people who devised reamers, I suppose, sort of figured that shop people aren't that smart. Condescending bunch of pricks. But shop people are that smart. And I mean, you don't have to have a master's degree to figure out that this tiny 1/8 of an inch reamer is not going to require the same amount of material left in the hole as a 1/4 inch reamer would. It just doesn't make sense. If I left a 1/64 of an inch material in the hole for this tiny, tiny reamer, I don't know if you can even see it on the screen, well, it's obvious that the flutes would get clogged up even before I got a 1/4 of an inch into the part. I mean, it just doesn't make sense. But 5% of this small tool is just as effective as 5% of this much, much larger tool. So use a percentage. Don't use the old over this and under that technique. It's not a good way to do it. Our second example here, well, we have 6mm hole to ream, and for that we're going to do the same thing. 6mm minus 5/100ths times 6mm. That gives me 5% smaller than 6mm, and this subtraction here gives me my final result of 5.7mm. Now, we said in 2 videos ago that you can have metric drills in all dimensions at increments of 0.1 millimeters. So if you wanted to use a 5.7, if you needed to use a 5.7mm, well, that 5.7 is available. But it's not part of a standard set. To get a metric standard set, something you'd find in most shops, well, it'll be in 0.5mm increments. So in this case, we'd want to go to a 5.5mm drill if it was a standard set. But a 5.7 is available. Or even closer, if we went for a 5.5, but we wanted something closer, well, take a look in your imperial sets. And the number 2 imperial drill is even closer to 5.7mm than the 5.5mm would be. So number 2 would probably be your best choice in the home shop for reaming a 6mm hole. So that's how we calculate 5% smaller, and a bit of an explanation of why it's important to do it this way and not the old way. There's one last thing that I think that needs to be mentioned here, and that is the fact that reaming gives us accurately dimensioned holes, but reaming does not position holes accurately. And that can be a pain, because when we're designing parts, we want to apply 2 basic rules, and that is preferred dimension design. We can call it PDD if you like to. And that preferred dimension design would state that when you're designing something, you shoot for whole numbers or whole fractions or something of the sort. If you figured out that you needed a 0.478 thousandths of an inch shaft, well, you'd never make the shaft 0.478. You'd make the shaft 0.5. It's a preferred dimension. So I think you see what I mean by that. And that's one reason that would make reamers interesting, because that preferred dimension applied with the second reason, which would be hole-based systems. It's much more difficult to produce an odd-sized hole than it is to produce an odd-sized shaft. And that is why when we design, we usually apply hole-based systems. And that means that if I have a hole into which a shaft must be inserted, well, I'm going to design it so that the hole is the base dimension, the preferred dimension. So let's say it was a 1-inch assembly, 1-inch hole, 1-inch shaft, and I wanted a little clearance. Well, I'd make the hole exactly 1 inch, or very slightly larger, but not smaller, and I'd make the shaft 1 inch a little smaller. Okay, I make the shaft slightly undersized to get my fit. Well, that makes using reamers really interesting because obviously a preferred dimension that's a hole-based dimension, well, would be easily attained with reamers. I mean, that's basically what they're made for. But I can't use them when the hole has to be accurately positioned. I have to bore the holes out. And that's long and tedious and difficult to get the exact dimension. At least much more difficult than it is with a reamer. So what we'll do is I'm going to go sit down because I'm getting old, and I'll explain to you a little trick about how to use reamers and still get very, very accurate positioning without all that much work. So wouldn't it be nice if we could use reamers to position holes accurately? Well, you can, but you'd have to use a little trick. Now, first off, let's explain. Reamers don't position holes accurately because they follow the pre-drilled hole, and drilling isn't an incredibly accurate method for positioning holes on a part. Now, we're talking very accurate. I mean, drilling is a good way to position, but if we're looking for a hole to be positioned within a few 10,000ths of an inch, drilling just will not give you that kind of accuracy. So what do we have in our arsenal for positioning? Well, we have boring bars. We have boring mark, and we have boring bars. So here's an example of a boring head that we could use in a mill that we'll get around to looking at eventually in a video lesson on milling machines. But we have a boring head in which is mounted a single lip cutter. And that single lip cutter will follow the axis of the machine and not the pre-drilled hole that it's enlarging, because it's a single lip cutter. It can't follow the hole. It has to be forced to follow the axis. And if your mill is good and square and your positioning of the table is good and accurate, well, you'll position a hole quite accurately. And what does that mean? That means that you're going to pre-drill a hole before you use this. The pre-drilled hole might be 1/1000th or 2 out in any direction, but when you bore to finish that hole, you will bring it back to its proper center position. So we have boring heads with boring bars. And on the lathe, well, we can dispense with the boring head and go straight to a boring bar. And if your lathe is good and straight and your part is turning concentric in the way that it should, well, you will be able to bore out an accurately positioned hole on the lathe. The problem with boring is that it positions properly. Yay! But it's a real pain as far as dimensions go. There is a lot of measuring, cutting, and adjusting. Boring bars are long, delicate tools, and they tend to deflect a lot, and they tend to chatter a lot, and they have to be adjusted very finely, and you have to cut and measure and cut and measure. And that's fine if you have no choice, but wouldn't it be nice to be able to use a reamer? Well, you can, if you combine the best of both worlds. Combine what's good with a boring head to what's good with a reamer. So if you have a hole-based design preferred dimension, and let's say it's 3/4 of an inch, and you have a 3/4 of an inch reamer, but it has to be really concentric, well, what you can do is drill that hole out smaller than 3/4 of an inch. We've just calculated 5%. Maybe I would drill it out 10% smaller. Once it's drilled out, I would mount a boring bar into my tool holder on the lathe, because I'm giving a lathe example here, and I would then bore that hole to bring it back true. And in doing so, I would bring the hole to somewhere around 5% smaller than its final dimension. What would I have at that point? Well, I'd have a hole that is truly parallel and truly at its proper position, but not at its final dimension. So instead of fiddling around with the boring bar for those last few cuts to get everything honky-dory, Well, what would I do? I'd replace the boring bar, I'd install my reamer, and I'd ream the hole to its finished dimension. Really simple. The reamer will give me that accurate diameter, no fiddling. And it will be positioned very accurately because the hole that it's following has been bored. Yeah, sorry. See, this is getting a little long, so I'm starting to fumble my words around. So I think that's enough. I was hoping that there'd be only 2 or 3 parts to this lesson 8 video. I couldn't imagine that I had that much to say about drill presses, but I guess there's going to be a lot more. This is the end of part 3. So until we meet again, probably with part 4 of our lesson 8 on drill presses, where hopefully we're going to get around to looking at countersinking, counterboring, spot facing, and tapping. Well, until then, have fun, be safe, and happy machining.